invertible matrix. How do I solve it? I want to solve it as a convex hull problem. So suppose that we are lucky and x to begin with is bigger than or equal, the solution is non-negative. Okay? It's like the triangle, the first problem that I gave, where we have a triangle, we know a point is inside. I know all the coefficients, the multipliers, whatever you call them, are non-negative. Now, in this case, we know that we know that this is empty because A is invertible. Since A is invertible, the only solution to AY equal to 0 is 0. So this means that I can apply the triangle algorithm to approximate 0 in this convex hull. So I compute such a point and use this theorem that I have, the sensitivity theorem, to test to what accuracy to solve this problem. And then we just simply divide by alpha n plus 1. In practice, we don't even need to use this sensitivity theorem. We simply run the algorithm, and in each iteration, as I get p prime, I divide it by the corresponding alpha n plus 1 to see how close it is to 0. Now, case 2, I want to solve Ax equals to b, where A is invertible, but I don't know if the solution is bigger than or equal to 0. Okay. So here I try to estimate the negative component of the solution. And to do so, let E be the vector of 1s in R to the n. There exists a t bigger than or equal to 0 such that if x is the solution to this, then x is bigger than or equal to 0, right? This is obvious. I'm just shifting the solution here. So let u be a times e, which is non-zero. Then the following is solvable. This system is solvable. Ax equal to b plus tu. Now here x is non-negative. So the only thing that I did is I changed the right-hand side from b to b plus tu. And suppose that t star is the minimum value of these t's, of the t which makes this possible. Okay? If I happen to know a value where t is bigger than or equal to t star, then we can simply apply the two-phase algorithm to solve this. Okay? So in this case, the problem reduces to the first thing. And the complexity analysis, the only thing is that t plays a role. I have to plug this in to the complexity analysis. So because my b of t changes to b plus t times u. U is bounded by t. Maybe we don't know how big this would be. Here is a theorem that I found, and maybe it's it's a valid question, I guess, to ask, but I don't know if people have studied this before. Suppose we have ax equals to b, and we look at the solution, and look at xi as the ith component of x. I want to know how negative can it be. Can I put a lower bound on this in terms of a? If I let Q be this matrix, symmetric, positive, definite matrix, A is invertible here, and W to be here, and let the ith column of Q be denoted by little q sub I, and pick the minimum of these, then, and lambda min is the minimum of this eigenvalue of Q, then I can show that xi is bigger than or equal to these. So, this gives a theoretical kind of a lower bound. I don't know the relationship between, say, these numbers, and say the condition number of a matrix. But maybe they are somehow connected. And as I mentioned, I haven't seen a theorem, but it's easy to prove. But I haven't seen a theorem in, say, numerical analysis books where they try to find the most negative component of the solution. Now, so once I find this, then I go back and convert it into a convex Hall problem and solve it like before. Then there is this incremental, what I call incremental triangle algorithm, which does the following. Rather than using a priori estimate of the least coordinate of the solution, we build up this estimate iteratively. How do we do that? Like this. So you give me a system, AX equals to B. Here, you give me the system, so maybe this is the most general one. I want to solve this. I know nothing about X. Okay? So I try to apply the triangle algorithm. Okay, so initially I let T0 be equal to 0. And suppose I attempt to compute a solution, x0, so that this is satisfied, using this two-phase algorithm, two-phase triangle algorithm. What can happen? If this is possible, we're done. So we just solving this two-phase algorithm. If not, this means that 0 is not in the convex hull of these points by the duality which I proved. So where P of t is this. Which means that by the distance duality, the triangle algorithm computes a witness with respect to this. In other words, it computes a point P prime of T0 in this convex hull such that these strict inequalities are satisfied. Strict inequality, the distances compared with this and the distances compared with this. So all these are strict inequalities. Now in this incremental approach, so again, let me just summarize again here. I try to solve Ax equals to B as if it has a non-negative solution. I use the two-phase triangle algorithm. If it doesn't fail, I'm done. If it fails, then in the process and by the duality, I have computed the witness, which means I have a point satisfying these strict inequalities. Now, I increase the t value until one of these inequalities reverses this direction, becomes bigger than or equal to. This means I can start pivoting again. I can start iterating again. So that's what I call incremental triangle algorithm. It tries to increase t until one of these constraints becomes an equality. This creates a new pivot point to see if the new system is solvable. The process is repeated. And some remarks that the incremental algorithm avoids using an a priori estimate of t star. It increases t incrementally, starting with t equal to 0, generating a sequence of approximate solutions that converge to the solution of Ax equals to b. The increase in t value in the incremental algorithm is done conservatively. I don't want to, I mean, you could say, okay, pick t equal to 1, double it to 4, and so on. And you can do it that way too. But I don't want to, that would be another alternative. So the potential advantage is that once, for a particular value of t, we get a witness p prime, meaning that the system wasn't solvable. For the next value, t prime, if it's still not sufficiently large, it would only do a few iterations. But I mean, this is intuitively makes sense. So other approaches are possible. Related work and future work, an algorithm for a variation of problem P where the coordinates of the point P is unknown, but the distances are given. So imagine you have a system Ax equals to B, and you don't know B, but you know the distance between B to the columns of A. This may happen to be, for instance, if A is an orthogonal matrix, then we know the distances. So I have a paper on this in a computational geometry conference called Looking for a Lost Treasure from Known Distances, because it's like that. I tell you there is a treasure in this room, and I don't give you the coordinates, but I tell you its distance from each of the corners is so much. Maybe I'm lying to you, and you would have to find out for yourself if I'm lying to you or if there is such an actual location physically existing. Triangle algorithm for special cases of Ax equals to b. There are maybe very special matrices. And here is one of the forthcoming papers that gives an actually polynomial-time algorithm for bipartite perfect matching. Bipartite perfect matching is one of the well-studied problems in computer science, and there are many algorithms. Most of them are graph theoretic. Here I'm going to give a very simple geometric algorithm for testing if there is a bipartite perfect matching. Sorry?
Is it better than max?
Not necessarily, no. It's not necessarily as fast. I mean, it could be slower. But it's a polynomial-time algorithm, and that's what matters, I think. I will get back to these worst-case complexities and generalizations of this. And they are here, is what I would like to mention. The complexity, the thing to, maybe one can, about this, remember that I have a set V1 through Vn, and the complexity of each iteration is O of Mn in the worst case, and the number of operations is O of 1 over epsilon squared. But this is for the convex Hall problem. Now, these are the worst case complexities. Could this be 1 over epsilon, for instance? That's one question. Another question is that as I go from, so if I start with a particular point P prime, I compute maybe all the distances to the VI's, and then I decide to get somewhere to P double prime. Next time I do this for P double prime, is it the case that I could use the information I have already gained, the distances, with respect to the Voronoi cells? Could that be used? So there are definitely open questions on this, but I think the potentials are there, that this algorithm is useful for solving, say, linear systems, and for the feasibility problem, and for linear programming itself. For instance, in polynomial-time algorithms for linear programming, one of the problems that it needs to be solved is a large system, linear system, yes, within, say, Newton's method. So instead of, and we need to solve a sequence of such a systems. Instead of solving them exactly, we could use the triangle algorithm to solve them approximately within epsilon. So, and then, when you look at, for instance, things like Jacobi method, Gauss-Seidel, the SOR, I was speaking to one of our numerical analysts, Professor Rector, about this paper. He hasn't read it completely, but he said it looks interesting compared with, say, conjugate gradient method. Conjugate gradient method is a method for solving a positive definite system. And the complexity in theory, it solves the problem in O of n iterations, each of complexity O of n squared. But in practice, the iterations depend upon the condition number. So, I mean, I think this, one of the things that I must say I have not seen in the context of iterative methods, the classical, well-known methods for solving linear systems, is a precise complexity result. Given epsilon, how many iterations, for instance, is it needed? And from my limited understanding on these iterative methods, it seems like you must have conditions on the matrices. For instance, diagonal dominance before, or certain decomposition, so that some diagonal dominance condition is satisfied. So how do I feel about this triangle algorithm? I don't have a lot of computation. I don't have, say, nothing, no serious computational result. But I think there are potentials. And I would find that hard to believe that it cannot compare with some of the existing methods for solving linear systems. or even solving this, for instance, simplex method.
Even for just linear algebra without any applications to LP, you think it still could be competitive? That's for the linear algebra without
LP?
Yeah, without combining it with linear programming.
Yes, I think it could compare for linear. I mean, let me suggest, go back to the same problem, the triangle.
Yeah.
The triangle. The other point, I want to know if this is in the convex hull or not.
Yeah.
I like to do this actually, I haven't done it, but I would like to see how the simplex method would do it on this.
Yeah.
The simplex method would convert this into an optimization problem.
Yeah.
And then it does that, it solves it, and at the end it says it's feasible or it's not, depending upon it. Now you could help the simplex method. You would say, okay, I'm going to let you to, within each iteration, to come up with an approximation to a point in the convex hull. I haven't done that, but I intend to do that. And I doubt that would do better than the triangle algorithm, really. So I think that, yes, I think that even compared with the simplex method doesn't really give you an estimate of how close you're getting to the optimal point. Here, every time I'm getting some information. I mean, like you visualize this room, you're trying to hide in this room somebody, you know, and we hire, Spider-Man, put him everywhere. He's going to find it, just looking at the corners here. One more thing that I can say, and then I'm done, is that this suggests even interesting possibilities, this triangle algorithm. Let's say I have a rectangle, and I have a point which is, let's say, I put the point here. This is P, and I start with P prime here. I had an REU student, and I had him do some visualization with this last summer. It turns out to be interesting. It's like mathematical art. But here, let's say you start with this, you go here. Then you use that, you're here. Then you go there, and you're here. And you may think, well, you're slowing down. What can you do? Create artificial vertices. You have Vi and Vj. Create new points, Vi, Vj over 2. You know, you're only adding a polynomial number. So it really gives rise to possibilities. And who knows? How are we, I mean, I may ask a question from someone who's a linear programming expert, and say, how do we really expect to find a fully polynomial-time algorithm for linear programming if it's solving this convex hull problem? That algorithm at some point has to recognize a bunch of vertices that are being used. Okay? If I have, say, 100 points, that's to find in the plane, that's to find the triangle. So you just use this. How is it going to do that? So the polynomial-time algorithm would, strong polynomial would have to recognize which ones to use. And then you can say, I could solve it by solving a linear system if I want to. So I know I'm there time-wise, and I will stop right here.
Thank you very much.
Thank you.
For the time, try a bit late to answer questions in private. Thank you.